Okay, so I want to start with something that sounds almost like magic. If you have ever heard of word to vec, there is this one famous example that is king minus man plus woman equals queen. Like mathematically, it is something they quote. So you subtract the concept of man from the word king and add the concept of woman, and you end up at queen. And the first time I heard that, I was like, wait, how? Words are not numbers, right? And you can't do arithmetic on words, except apparently you can. And that's exactly what this video is about. Today, we are going to understand how that's possible, what embeddings actually are, and why they power basically everything in modern AI, that is, search, recommendations, ChatGPT, all of it. Let me just back up. Before we get into the fancy math, let's just get the core idea. An embedding is a way of converting something, that is a word, a sentence, an image, a user's behavior, into a list of numbers. That's it. It sounds a little underwhelming, right? But here's the key thing. The numbers aren't random. They're chosen so that similar things have similar numbers. So for example, if you take the word dog and the word puppy, their list of numbers will be really close to each other, but the word dog and skyscraper, those will be pretty far apart. We call this list of numbers a vector, and all of these vectors live in what we call a vector space, which is basically a mathematical coordinate system, except instead of 2 or 3 dimensions like how you would draw on a paper, it might have 384 dimensions or 1536 or more. So that's where the actual magic happens. Now, how do we actually get from a word to a vector? The naive approach would be something like this. Imagine we have 10,000 words in our vocabulary, and for each word, we create a list of 10,000 numbers. Almost all of them are zeros except for a single one. So, for example, we have word number 42, which would have 1 in position 42, and that's it. So, this is called one hot encoding. The problem with this is that every word ends up equally distant from every other word. For example, king and queen are treated just as unrelated as king and pizza. The representation contains no information about meaning or similarity. So the real breakthrough came through training neural networks on real language. Models like word2vec and later transformers learned by looking at context. In other words, which words tend to appear near each other in actual text. And something really interesting happened there. When you train a model this way, the numbers it learns for each word starts to capture meaning automatically. Words that appear in similar contexts end up with similar vectors. For example, doctors and nurse might appear near words like hospital and patients or treatments, so their vectors become close together. This idea is called distributional hypothesis. Basically, words used in similar contexts tend to have similar meanings. And honestly, that simple idea is underneath almost everything happening in modern AI language models. Okay, so let's make this visual. Imagine a giant multi-dimensional space. Real embedding vectors might have hundreds of dimensions, like 512 or even more, but obviously we can't draw all that. So for visualization, let's squash everything down into 2D. Now imagine every word is a dot in the space, and something really interesting starts to happen. Words with related meanings naturally cluster together. Paris, London, and Tokyo end up together because they're all cities. Dog, cat, and puppy form their own cluster. Sad, unhappy, and miserable hang out together somewhere else. The geometry starts reflecting meaning. But it gets even cooler than that. The directions inside this space also starts to mean something. For example, the direction from man to woman is surprisingly similar to the direction from king to queen, and also similar to the direction from actor to actress. So there's this consistent gender direction embedded in the geometry of the space, and that's where this famous equation actually works. King minus man plus woman lands somewhere near queen. You can think of it like a vector arithmetic. You start at the king, subtract the male component of it, and then it starts moving to the female direction, and the result ends up close to queen. So these embeddings are not just random list of numbers. The space itself has structure. It encodes relationships, concepts, and patterns about how language works. Now you might be thinking, okay, so things that are similar are close in this space, but how do we actually measure closeness? You might think just measure distance between 2 points, right? Euclidean distance, like how we did it in school. And sometimes people do that, but the more common approach is cosine similarity. Instead of measuring how far apart 2 points are, we measure the angle between the arrows from the origin to the each point. If two vectors point in the same direction, which is the angle of 0, then the cosine similarity is 1, which means a perfect match. If they are perpendicular, it means there is no relationship, and obviously it's 0. If they point in opposite direction, it's -1, meaning they are opposite in meaning. Why angle instead of distance is the next question that we might get, because we care more about the direction than magnitude. A short document and a long document about the same topic should still be similar, even if one vector is technically longer. So where do embeddings actually come from today? The older word-to-vec style models gave one embedding per word, that is just one fixed vector, no matter where the word appeared. But language doesn't really work that way, right? Take the word bank. In the phrase river bank, it refers to the side of a river, and in the phrase in bank account, it refers to a financial institution. Completely different meanings, same exact word. Modern embedding models solve this using context. So instead of embedding a single word by itself, the model processes the entire sentence or a paragraph or a chunk of text using a transformer network. And what comes out is a vector representing the meaning of that text in context. So the sentence, I sat by the bank of the river, produces a very different embedding from I need to call my bank. Even though both contain the word bank, the surrounding words completely change the meaning. The transformer looks at all of those surrounding words when building the embedding. And this is really big. It means the model is no longer reacting to keywords, it's capturing intent and meaning. And the embedding reflects what you meant, not just the little words you typed. And you might be wondering, in a 512 dimensional embedding, what do those 512 number actually mean, right? And this is where things get a little humbling. We don't fully know. Those dimensions are not neatly labeled. It's not like dimension 1 means sentiment, dimension 2 means topic, dimension 3 means formality. That's not how these models work. The network model learns its own internal way of organizing information across all of those dimensions, and most of the time, that organization is not directly human interpretable. Researchers have discovered that some directions in embedding space correspond to recognizable concepts. For example, we talked earlier about the gender direction from man to woman, right? So that's one case. But in most cases, meaning is spread across many dimensions at the same time. And this is called a distributed representation. So instead of storing one concept in one location, the model distributes information across the entire vector. And honestly, that's part of what makes embedding so powerful. The model is free to organize information in whatever way it helps make better predictions. It does not need to structure the knowledge in a way that feels intuitive to humans. So even though these vectors can look mysterious, the geometry they create turns out to be very useful. So that's what embeddings are and how they are made of. Now, what do you actually do with them? This is where it gets really practical, because once you can represent any piece of text as a vector, you can unlock a bunch of really powerful capabilities. Search that understands meaning, recommendations, clustering documents, detecting duplicates, and the big one right now is the RAG, that is Retrieval-Augmented Generation. So let's go through each of these. Okay, so a classical keyword search works like this. You type heart attack symptoms, and the search engine looks for documents that literally contain those words. But what if a document says something like myocardial infarction warning signs? Basically, it's the same thing, but it is completely different words. So what happens? Keyword search misses it, but semantic search fixes this. You embed the user's query into vector. You've already embedded all of your documents into vectors. Now you just have to find the documents whose vectors are closest to the query vector using what we know as cosine similarity. And because the embeddings capture meaning, not just words, heart attack symptoms and myocardial infarction warning signs will have very similar vectors. So, they'll find each other. This is what modern search is built on. Notion, Linear, Obsidian, GitHub Copilot. They're all doing the same under the hood. Okay, so imagine you have a million documents all embedded into vectors. When a query comes in, how do you find the nearest vectors fast? You can't just compare the query to every single document, right? That's a million dot products per query and it would be way too slow. So this is where vector databases come in. Tools like Pinecone, Weaviate, qdrant, pgvector. These are databases specifically designed to store vectors and run approximate nearest neighbor search very efficiently. They use clever indexing techniques like hierarchical navigable small words, also known as HNSW, to pre-organize the vector space so lookups are actually fast. You don't need to understand the full algorithm, but the mental model is that instead of searching everything, the database navigates through a smart graph structure to find the closest vectors in milliseconds. Of course, even across millions of entries. Okay, this one's huge. Retrieval augmented generation. The basic problem it solves is that language models have a knowledge cutoff. They can't know about your company's internal documentations, your recent emails, last week's products update. But with RAG, here's what you do. You take all your documents, embed them, store them into a vector data space. When someone asks a question, you embed the question, search the vector database for most relevant documents, and then you stuff those documents into the prompt alongside the question. Now the LLM can answer based on your actual documents. It's not memorizing your data, it's retrieving it on demand and reasoning over it. This is why every enterprise AI product right now is basically built on top of embeddings. It's the infrastructure layer. Understanding the embedding means understanding the foundation of how basically all of these tools work. One thing that trips people up is the off-shelf embedding models that are trained on general internet text. That's great for most things, but if you are building a medical search tool, for example, or a legal document search, or of course a code-based search, general embeddings might not understand the domain well enough. Let's say we have an example of pleural effusion and fluid in lungs might not score as similar as they should, right? Because medical text wasn't well represented in the training. So the solution is fine-tuning. You take a base embedding model and continue training it on your domain-specific data, using examples of what should be similar and what shouldn't. This is called contrastive learning, and it can dramatically improve performance for specialized use cases. It's not always necessary, but it's worth knowing the option exists. Here's something that blows people's mind when they first hear it. You don't have to limit embeddings to text. Models like CLIP or CLIP from OpenAI map both images and text into the same vector space. So the vector for the text a dog running on a beach ends up very close to a vector for an actual photo of a dog running on a beach. Same space, different modalities. This is how Google image search works when you type a description and get images. This is how AI image generation models understand your prompts. And this is how you search a photo library using natural language. The abstraction generalizes completely. Any data like audio, video, code, even molecular structures can be embedded into vectors if you train the right model. Embeddings are really just a general purpose representation format. That's it. Okay, let's bring it all together. Embeddings are vectors, that is a list of numbers that encode meaning. Similar things have similar vectors. We measure similarity with cosine similarity. Modern embedding models like BERT and Text Embedding 3 generate contextual embeddings that understand full sentences. And on top of that, you build semantic search, vector databases, RAG systems, multimodal search, basically the entire modern AI application stack. The king minus man plus woman equals queen example. Now you can see exactly how that works, right? You are doing an arithmetic on meaning, and that's what makes this idea so powerful and so strange at the same time. If you want to go deeper on this, next I would suggest watching the video on transformers because understanding how embeddings are generated takes you directly into how attention works. Hit subscribe if this video was useful. Thank you. I'll see you in the next one.